Okay, so let's jump right into it. Um, Today's plan, finish chapter 8, particularly section 8.8, the complex number system, and then start into chapter 9, working with quadratic equations. So we've seen a little bit of solving quadratic equations before. We're going to look a little more deeply at solving quadratic equations today and in the next couple classes. And the quote of the day today, well, there's two quotes of the day. I don't know what my thing has been with two quotes of the day for the last few classes, um, but as we're heading into the kind of home stretch of the course, we have a lot of prep for final exams, projects, papers, those kind of things coming up. I thought both of these are ideas that we had discussed before, but I thought both were pertinent. Um, One from my favorite professor, Bill Layton, good decisions come with experience, and experience comes from making bad decisions. So if there's anything to this point in the semester that you look back and you say, I wish I had done that differently, or I wasn't so happy with the result of that decision, uh, how can you, looking forward over the next few weeks, make a change that, maybe makes final exams easier for you or gets the final project out of the way in a less stressful way, something like that. And I think related to that idea is, a different quote on margin than the one we saw before, but you must create more margin so that you have room for what's important, not merely urgent. So we do have Thanksgiving break coming up next week. That's, super nice that we have a week of no classes. But, you might want to put in a little bit of work over Thanksgiving break. It's going to be really hard to kind of completely step away from all your courses, come back, and then we only have a week of classes before final exam week. So it's going to be really hard to get that momentum back up in just 1 week. Can you put in a little bit of time over Thanksgiving break? Certainly not saying to, you know, work yourself hard or harder than a typical week, take a bit of a break, but can you maybe on Tuesday spend a little time knocking out a couple homework sets or, getting a draft of a paper ready and maybe on Saturday, make a plan to study for final exams and, something like that. Can you put in a little bit of work so you're kind of touching base with the material, kind of keeping that momentum up and finishing strong. And then when we hit December 13th or whatever it is, I think it's Friday the 13th, right? When we hit December 13th, and final exam week is over, and then you know, then you can just brain dump and relax after that point. So, but can you do something in the next couple weeks to create more margin for yourself during final exam week to make things less stressful, to make things go more smoothly, and just generally to have a more successful week that week. Okay, so we're finishing up discussing the complex number system, and we talked about adding, subtracting, and multiplying complex numbers last time. So we're going to continue on with multiplying complex numbers here. So let's suppose we want to simplify -6 minus 5i all squared. Well, we do have to be a little careful here. We don't want to, make the mistake of making this say -6 squared minus 5i squared or something like that. This is -6 minus 5i times -6 minus 5i. And if we FOIL this, we get -6 times -6 is positive 36. Our outside gives us -6 times -5i, so that's plus 30i. Inside also gives us plus 30i. And our last give us, well, -5 times -5 is plus 25. And I times I is I squared. Or this is 36 plus 60i plus 25 I squared. Now, if we look at this, we might feel like this is simplified, like it's in simplest form. I have uh, three terms. Each one has uh, something like a variable. We have constant I or I squared, and it's the different powers. But I, sometimes we move it around kind of like it's a variable. But remember, it has this special property that I squared equals -1. And remember I said that the complex numbers, a plus bi, are closed under addition, subtraction, but also multiplication and division. In other words, I should be able to simplify this down even further to something that's like a plus bi. And I'm going to use this I squared equals -1 property to say, wait, well, I have an I squared here. That's just a -1. I can replace that by -1. So really this 25i squared is just a minus 25 with no i's. 36 minus 25 is 11 plus 60i. Now, what about a square root problem like this? Square root of -4 times square root of -16. I think I mentioned last time as an exercise maybe to take a look at this problem and it kind of take two paths. In one path, try to first convert everything to the imaginary format and then do the multiplication. And second, try using the square root property where square root of a times square root of b equals square root of a times b. Now that property only applies when a and b are positive, but is that really a necessary restriction? Well, let's see. So if I do the kind of right way, so to speak, square root of -4 would be I times the square root of 4. And square root of -16 would be I times the square root of 16. Or that is I times 2 times I times 4, or that is 8i squared, or -8. Now, if I try to, I'm going to put a question mark here. If I try to use my square root property, my product property for square roots, it doesn't technically apply here because we said it should only apply whenever everything is positive, all the inputs are positive. But maybe we think, maybe it does apply here and we can generalize that property. Well, here I would end up with square root of -4 times -16. But here my negatives would cancel. I'd have square root of 4 times 16. And that would be +2 times +4, or +8. We see +8 clearly not equal to -8. So we cannot generalize this. So we do have to be careful and respect the fact that this product property for square roots really only, we've only demonstrated that it applies when the inputs into the square roots are all positive. Okay, what about a problem like this? 4 minus 5i times 4 plus 5i. I know this is a special form. A minus b times a plus b turns into a squared minus b squared. Right, or we have 4 squared minus 5i all squared. So here I have 4 squared minus, now my exponent can distribute in, 5 squared times I squared, or that's 16, and then minus, well, this is 25i squared, and we remember that I squared is -1, so 16 plus 25, or 41. So we actually might notice something here, that if I take an imaginary number, say 4 plus 5i, or I should say a complex number in the terminology that we're using, 4 plus 5i. If I change the sign, plus or minus, on the imaginary term to make it 4 minus 5i, basically if I replace I with -i, in a sense, then when I FOIL, Well, my inside and my outside, what would contribute the I term, the imaginary part of the result, that exactly goes away. And I'm left with just the real number. So if I have a complex number, say z equals a plus bi, I have a special name for doing this process of replacing I with negative I or just switching the sign of the imaginary term. I call this the complex conjugate. Sometimes we write it as z bar. Sometimes we write a bar over the top of it. And this has the property that z times z bar is a real number. All right, we're going to leverage that in these next couple of problems. So here I have 3 minus 2i, all divided by 6 plus I. Now, when I say simplify in a complex number scenario, I mean write this as a plus bi. Write it as real number plus real number times I. Now, when I was adding, subtracting, or multiplying two complex numbers, that wasn't too bad to do. I mean, I maybe had to do a little bit of simplification with an I squared or something like that, but I didn't have to do anything, super creative. I didn't have to put too much into the system. I just had to kind of do the arithmetic operations and follow it where it led. Here, though, I noticed that this doesn't work so nicely. I mean, 3 minus 2i over 6 plus I, should I do some kind of long division? It doesn't feel like that's going to work very well, like something like polynomial long division, but the real part and the imaginary part aren't really doing kind of the same thing. So what should my approach be here? Well, I realized that if I multiply top and bottom by the complex conjugate of the denominator, that will give me a denominator that's just a real number. So that might be a nice thing to do first, right? We saw this in rationalizing the denominator in earlier work, getting rid of square roots in the denominator. We're going to do a similar kind of thing here. I'm going to multiply the denominator by the complex conjugate of 6 plus I, which is 6 minus I. And if I multiply that on the bottom, of course, I need to multiply by that on the top. In the denominator, I get 6 times 6 is 36. And then plus 6i minus 6i, the imaginary parts go away. And then I get minus I squared, or that's just plus 1. In the numerator, I get 3 times 6 is 18, minus 3i, minus 12i, and then plus 2 I squared. This plus 2 I squared becomes a minus 2. 18 minus 2 is 16 over 37. Plus what? Negative 3i minus 12i. I guess I'll write this as a minus 15 over 37i. And I do have real number plus real number times I. So I have a plus bi, where a is 16/37 and b is negative 15/37. So that's the trick to remember. Just like rationalizing the denominator, multiplying by the complex conjugate on the denominator gets rid of the imaginary part in the denominator, turns the denominator into a real number, and then we can simplify the numerator and break things apart into a single complex number. Now, what if I have something like this, 4 plus 3i over 7i? I only have an imaginary part in my denominator. Here, I suppose I could follow my previous rule and multiply by -7i on top and bottom. But I actually noticed that here I can get away with doing this a little more easily even. I see that to get rid of the complex bit in the denominator, that I just needs to hit another I. I can actually just multiply by I on top and bottom. In the denominator, I get 7i squared, or just -7. And in the top, I get 4i plus 3i squared, or -3. So that's what? 3 minus 4i over 7. Or I could write this a little nicer as 3/7 minus 4/7 I. Now, why wouldn't this work up here? Well, up here, if I try to multiply by an I, that just flip-flops which one of these terms has the imaginary part. It'll be 6i minus 1. I'm still in the same situation, right? So because I had two separate terms, one imaginary, one real, if I multiply by I still have one real, one imaginary. But down here, since I had a purely imaginary term, if I multiply by I, that turns it into a real term. Okay, any questions on any of this? And maybe one good little interesting tidbit is, what is 1 over I? So one little interesting piece of information is 1 over I turns out to be actually the same as -I. So dividing by I is the same as multiplying by -I. Maybe an interesting little factoid. That could have perhaps made this calculation here a little bit simpler. I probably still would recommend going through the calculation, the long way, because things like this are, is this worth taking the time and effort to memorize? Probably not, but just one little interesting thing about imaginary numbers. And now let's just look at powers of I. So we know that I, or say I to the first, is of course I. And I squared is -1. Well, I cubed nicely is I squared times I, but that's just -I. And I to the fourth, well, that's like I squared squared. That's like -1 squared is +1. And then I to the fifth, of course, is going to be I to the fourth times I, or just I. And we see we'll repeat the process. So the powers of I are cyclic every 4 powers. And as kind of a side note, the powers of I actually have this interesting, intricate relationship with sines and cosines, which are also cyclic. Um, and there's a very deep relationship between them, and they come up in things like wave equations and so on, where complex numbers kind of lead to oscillatory solutions. So there's a really deep idea here with these being cyclic. It's beyond the scope of this course, but we can see, for instance, that if I have I raised to a power, and that power is 4 or 8 or 12, 16, etc., if it's a multiple of 4, then that just turns into a 1. So for instance, I to the 36 36 is 9 times 4. This is like I to the 4th to the 9th power. Well, that's 1 to the 9th is just 1. I to the 37th then would be I to the 36 times I. I to the 38th, we pick up another factor of I to make I squared -1. I to the 39th, pick up yet another factor. -1 times I is -I. And I to the 40th, we're at I to the 4th to the 10th power. We are back at +1. Right, so I could look at a remainder after dividing by 4 for my power, and that's going to associate with one of these over here. Any questions on complex numbers? Okay, let's start into chapter 9 then. Okay, chapter 9, quadratic equations and functions. And we're looking at, to start off today, 9.1 and 9.2, solving quadratic equations using the square root property, and then looking at completing the square. So let's just jump right into a quadratic equation here. We want to solve x squared minus 4 equals 0. Now we know we can factor and use the zero product property here. So just as a reminder, let's come over here to the side. We could write this as x minus 2 times x plus 2 equals 0. And then we say either x minus 2 equals 0 or x plus 2 equals 0, x equals 2 or -2. How do we solve this using the square root property? One thing that I notice about this quadratic equation is, nicely enough, it has a quadratic term and a constant term, but no linear term. There's no term with just x in it here. What that means is I can isolate the variable more easily and then solve from here. Right? If I had something like x squared plus x equals 4, I don't really know what to do next once I isolate the variable. But if I have something like x squared equals 4, well, I can take square roots of both sides. So I would get something like x equals square root of 4, but I kind of know that if I put a positive number in and square it, that gives a positive output, but also if I put a negative in and square it, that gives a positive output. So I indicate that I have two solutions now, when I take the square root, a positive and a negative solution. I indicate that with a little plus minus kind of symbol in front of the square root in this case. Or I see that x equals plus or minus 2. And that's exactly what we expected from over here. So one thing when I'm using the square root property, I want to be careful to make sure to respect the fact that this equation solving step, take the square root of both sides, can lose a solution. Right? If I'm not careful, if I just made this x equals square root of 4 and then I get x equals 2, I've lost the solution to the original equation. So when I do this equation solving step of square root both sides, I need to be careful and maintain the same number of solutions by making sure I include a plus or minus when I square root. It's a little bit like when we had a radical equation and we squared both sides, we might introduce extraneous solutions. This is kind of that, just in reverse. When I square root, I might lose solutions if I'm not careful. So I need to just make sure to, anytime I square root both sides of an equation, put a plus or minus in. Now I could have something a little more complicated like this here. -5/3 x squared equals 60. To isolate the variable, well, I want to multiply by the reciprocal of -5/3, that's -3/5. So this is 60 times -3/5. Or I have x squared is 60 over 5 is 12 times -3 is -36. Now I have x squared equals negative number. 2 chapters ago or something, I would have not known what to do with this. I'd have said something like no real solutions, but after talking about complex numbers, we see, okay, we can actually handle this just fine. X is going to be plus or minus the square root of whatever's on the right-hand side. That happens to be -36. Be careful with where your pluses and minuses are. When we square root both sides, the -36 ends up inside the square root. And then because we square rooted both sides, we need to maintain our two solutions by sticking a plus or minus in front of the square root. This minus on the -36 doesn't like come out of the square root or something like that. And the plus or minus doesn't go inside the square root. So be careful with where the different signs are ending up with respect to the square root. But I know the square root of negative number is I times square root of the positive of that number. Oh, and then square root of 36 is just 6. So here we have x is plus or minus 6i, a purely imaginary solution. We could plug back into the original equation, check that everything works out, and it will check out. What if I take a step up in complexity? Have something like this. I don't just have an x squared. If I multiplied everything out, I would have a quadratic term from the first, and from the cross terms, I would have a linear term. So I don't just have an x squared term. However, if I zoom out a little bit, the only piece with a variable in it is this whole x minus 1/3 squared. I can isolate that variable term. If I really wanted to be pedantic, I could do something like y equals x minus 1/3. And then I have like y squared minus 7/9 equals 0. I don't think we need to go to that extent, but we could if we wanted to really make it look like, say, a problem like one of these previous ones. But I can isolate this variable term, x minus 1/3 squared, by adding 7/9 to both sides. And now I just have something squared on the left-hand side. To get the variable into a simpler form, I can square root both sides. So x minus 1/3 equals square root of 7/9. But again, remember, we need to have plus or minus that. And I might take a second to simplify this. I'm going to make this square root of 7. There's not much I can do with that, but the square root of 9 is 3. So x minus 1/3 is plus or minus square root of 7 over 3. Now I see that I have just a linear equation in one variable, right? Well, I have just a linear equation in one variable, and I solve that by just adding 1/3 to both sides. So it turns out that x is 1/3 plus or minus square root of 7 over 3, or I could write that as one fraction, 1 plus or minus square root of 7, all divided by 3. So even though I had a quadratic term and a linear term here, since they were kind of all hidden under this perfect square, things were actually just as easy to solve for me as if I didn't have the linear term at all. If I can hide that linear term under a perfect square, I can basically treat it like I'm solving one of these previous problems. Maybe there's another step or two at the end to get the final solution, but it's not, that's just solving a linear equation problem. That's not a very challenging part of the problem. And we could have something like this: 3x minus 1 all squared plus 9 equals 0. So again, I see that my variable is kind of tied up under this perfect square. So variable term plus constant term. Let me get that constant term to the other side. And now I want to make my variable side simpler. I can square root both sides. And I remember that when I square root both sides, when I do that equation solving step, very important, I need to put in a plus or minus, and I'll put it on that square root of -9 in front of the square root. Now let me simplify this right-hand side first before I go much further. So square root of -9, by definition, is I times the square root of 9. And square root of 9 we know how to deal with. That is just 3. So this is just 3i. So 3x minus 1 equals plus or minus 3i. Now this kind of looks strange because it has the plus or minus thing here and it has an imaginary number and all that. But really, kind of fundamentally, this is just a linear equation in x. Number times x plus number equals number. I mean, maybe that number on the right-hand side looks a little strange, has a plus or minus, has an imaginary unit, but we move it around basically just the same as any other number. So we would apply the same equation solving steps here, isolate the variable term by adding 1 to both sides. And then we isolate the variable by dividing by the coefficient. Oh, and that is my solution. X equals 1 plus or minus 3i over 3. And if I really wanted to be explicit about my two solutions, I might write x equals 1 plus 3i over 3, or x equals 1 minus 3i over 3. This is kind of the longhand version of what I've squeezed into the plus or minus notation over here. I just want to be very clear about that. Like when I'm writing x equals 1 plus or minus root 7 over 3, that represents two solutions: 1 plus root 7 over 3 and 1 minus root 7 over 3. Any questions on solving quadratic equations using the square root property? So the point is, if I have a quadratic equation like this, I can solve it pretty easily. But there are maybe surprisingly many quadratic equations that maybe don't look exactly like this, but look close enough to that we can solve using very similar techniques. Right. As a side note, we had a previous quote of the day where I talked about the value of mathematics is in its generalizability, that if I know how to solve this problem, if I deviate a little bit from this problem and ask a problem that's of a similar type, but maybe on the surface level looks quite different, my ability to solve problems that are nearby is still quite high if I understand the general idea. Right? If I understand the reason that this is a fairly easy quadratic equation to solve. I mean, I didn't have to do factoring or anything like that. I could if I wanted to in this case, but didn't have to. But what made this easy was the only place my variable showed up was inside of a perfect square. I have a problem like this that looks at the surface level very different from x squared minus 4 equals 0, but I still have the characteristic that anywhere that my variable shows up is inside a perfect square. And that is what makes it easy to solve. Right, so I recognize that if I understand the more general idea behind what makes this equation easy to solve, and you know, not just the specifics of why is it easy to solve? Well, it's easy to solve because x squared equals 4, and that's easy to solve, right? So now our question might be, well, what if I have a quadratic equation that doesn't look like one of these types where my variable is under a perfect square? What if I have a quadratic equation like this one? If I just kind of naively try the similar equation solving steps, isolate the variable, in this case, terms, two terms. Now what do? Do I like square root both sides? Well, that's not going to mesh well with the 6x. Well, maybe I should isolate the x squared, negative 6x plus 55. Do I square root both sides now? Well, now I just have a radical equation. It's almost, in a sense, even worse. So I can't just naively apply the same equation solving steps that I applied up here. But it would be really, really nice if this had the characteristic that everywhere that I see a variable, everywhere I see an x, it's underneath a perfect square. For instance, if I look at this one up here, if I multiply this out, what would I get? I would get 9x squared from 3x times 3x. My outside is going to be minus 3x. My inside is minus 3x, so that's minus 6x. My lasts are going to give me plus 1 plus 9 equals 0. Or I get 9x squared minus 6x plus 10 equals 0. I mean, if I multiply this out, this problem looks like that one. I could have asked you up here, solve this, 9x squared minus 6x plus 10 equals 0. And if you would have been able to reverse these steps and write it this way, wrapping all of the instances of x under a single squared term, well, you'd have been able to solve it the same way from this state. So the question is, how do I get from this state, ax squared plus bx plus c equals 0, into a state where I have both of my x terms wrapped under a single square? And the answer is, I do something called completing the square. So I noticed that if I have x plus a all squared, that turns into x squared plus, let me actually not make this a. Let's call it x plus r squared. We're going to kind of trademark a, b, and c a little bit later to mean certain things. So in the next couple sections. So we'll just call it x plus r squared. If I multiply this out, this is x squared plus 2rx plus r squared. So if I look at something like x squared plus 6x minus 55 equals 0, if I want to kind of make that look like x plus r squared for some r, what would that r have to be? Well, I see that 2r has to be 6. So this has to look like x plus 3 all squared. When I multiply out x plus 3 all squared, that gives me x squared for my first. My outers give me plus 3x. My inners give me plus 3x. So that's plus 6x. And then my last give me 9. Now, I have this problem of this minus 55 to deal with. I think there are two ways to deal with this. One is we can imagine splitting off part of this minus 55 to kind of contribute towards this perfect square and leaving some of it behind. I think that's a little bit confusing to kind of my way of thinking. Let me move this work down just a little bit. So what I would prefer to do, and this is, I think, more of a taste thing, but what I would prefer to do is to first move the 55 to the other side. Now I know that x plus 3 squared is what I want to get on the left side. I want this x squared plus 6x to turn into an x plus 3 all squared. But when I do that, I see that that adds 9 to the left side. So I need to add 9 to the right side as well. Okay. Or another way of thinking of this is if I think of the black work as kind of just scratch work that I was looking ahead a little bit, I can choose to add 9 to both sides. And what does this do? This makes my left-hand side a perfect square. And 55 plus 9 is 64. So this is the idea of completing the square. Now, personally, I like to think of it as isolate my variable terms, decide what I need to add onto my left side to make a perfect square. I can always do that. What I want to add on is take 1/2 the coefficient of the linear term and square it. That's what I need to add on to both sides. That makes the left side a perfect square. Write the left side as a perfect square. So x plus 3 all squared and equals number, whatever the right side turns out to be. It might be a nice number like this one. It might be a messier number, but still just a number. I can square root both sides now. X plus 3 equals, I have square root of 64 on the right. And again, I have to remember that I applied the equation solving step of taking the square root of both sides. But if I don't correct for the plus or minus solution, I would lose a solution. So I stick a plus or minus in front of there. I have x plus 3 equals plus or minus root 64 is 8. And now I solve for x just by solving a linear equation. X equals -3 plus or minus 8. Now, in a situation like this where I can simplify things completely, I will go ahead and simplify this. So x equals -3 minus 8 is -11, or x equals -3 plus 8, x equals 5. Okay, let's look at this next example. So here we want to solve 2x squared plus 4x equals -16. Now I can go ahead and start trying to complete my square right away, but I noticed that it's going to be kind of complicated because I have a 2x squared. Maybe the first thing that I'll do is choose to divide both sides by 2. So that gives me x squared plus 2x equals -8. Just like I pointed out above, I want to make this x plus something squared, that means my cross term, my linear term, has to have a coefficient of twice the thing that I want inside of there. So 2 has to be 2r, or r is 1. And then I want to add on r squared. So I want this to be x plus 1 all squared. That gives me x squared plus x from the outside and inside. So plus 2x, so that matches up correctly. Plus 1 from my lasts equals -8 plus 1. If I square root both sides, I have x plus 1 equals square root. -8 plus 1 is -7. And I better put a plus or minus on there so I maintain my two solutions. At this point, I'll isolate my variable term. X equals -1 plus or minus. And I'll rewrite this square root of -7 as square root of 7 times I. And I've isolated my variable term, but because the coefficient was 1, I've also isolated my variable itself. And I have my final answer. Okay, what about a problem like this? So x squared minus 3x equals 2. So these couple up here, the cross term kind of worked pretty nicely. I got x plus 3 squared or x plus 1 squared, kind of worked pretty nicely with our completing the square process. This one's not going to work so nicely. Right, I want to end up with, say, x plus r squared, which is x squared plus 2rx plus r squared. So I need 2r to be -3, or r has to be -3/2. So I think I'm actually going to want this left-hand side. I've already got the quadratic and linear terms by themselves. The constant is on the other side. So I think I'm going to want this to be x minus 3/2 all squared. When I multiply this out, the first will give me x times x or x squared. That looks good. My outsides will give me -3/2 x. My insides will give me minus another 3/2 x. -3/2 minus 3/2 does give me -3x, which is exactly what I want. Now I'm going to have a constant term of plus 9/4 plus 3/2 squared. So inside of this blue term here, when I multiply it out, there's a plus 9/4. So I've effectively added 9/4 to the left-hand side when completing this square. So I have to add it to the right-hand side as well. If you wanted to do an intermediate step where you figure out that 9/4 is what I need to add to both sides, add it to both sides, and then rewrite the left side as a perfect square, that's perfectly fine. But I see I have x minus 3/2 all squared equals 2 plus 9/4. On the right-hand side, 2 is 8/4 plus 9/4 is 17/4. And we want to, oh, I didn't leave myself enough room. 17/4. And we want to square root that. So I have x minus 3/2 square rooting gives me x minus 3/2, and on the right-hand side, square rooting gives me a square root of 17/4. And I make sure to stick my plus or minus in there to maintain my two solutions. I have x equals 3/2 plus or minus, and the square root of 17/4, I can write a square root of 17 over 2, or I can write x equals 3 plus or minus root 17 over 2. I think that is the best I can do. Any questions so far?
How did we get 17?
Yeah, good question. So this right-hand side over here, 2 plus 9/4. 2 is 8/4. And 9 plus 8 is 17 over 4. Yep. So that 2 is what gave us the 8/4. And then 9 plus 8 gives us the 17. And this 9/4 came from the fact that 3/2 squared is 9/4. That was the constant term that we had to add onto the left side to turn this into a perfect square. Now, as a side note, we might not recognize this as a perfect square or a start of a perfect square binomial. It's not a perfect square over the integers. It's not like, x minus 2 squared or x plus 3 squared or something. But it's a perfect square over the fractions, over the rational numbers. So another point that I think is valid to think about is, something like this, we could solve this by factoring, right? We could have factored this. We would have seen that it would have factored into what, x plus 11 times x minus 5. Find two numbers that multiply to negative 55 and add to 6. But this one, we wouldn't have been able to factor. If we put everything on the left side and made it 2x squared plus 4x plus 16 equals 0, we wouldn't have been able to factor that. Same with this one. We wouldn't have been able to factor this one. Not over the integers anyway. So the methods we're investigating here, they allow us to solve problems like this that we could factor. We could solve this one by factoring from previous work, or we could solve this one by factoring if we wanted to. But the other three up here, we would not be able to solve by factoring. Right? We could solve this one by factoring, but we could not solve these next two by factoring. So we're able to solve using this completing the square method more quadratic equations that we were able to solve before. Before, we were only really able to solve ones that I had carefully cherry picked. I didn't really tell you I was carefully cherry picking them, but I carefully cherry picked ones that yielded a quadratic equation that we could factor and solve. But something like this, we wouldn't be able to factor, but using the completing the square method, we can still solve it. So we can use this method to solve all of the ones we could solve previously. If we wanted to use this method, we'd have a choice between the two methods. But this completing the square method solves other quadratic equations that we wouldn't have been able to solve with just the factoring over the integers method. Right, and if you wanted to try, write these out in terms of stuff equals 0 and try to factor them, right? Go through and try to find out how to take that left-hand side, ax squared plus bx plus c, and get a factorization for it, right? Write out all of the products that say multiply to c or ac, and then see if you can find any that add to b. And you're going to see that you're going to end up with a quote prime a quadratic function in these two cases. Now, in the first case, you could do that. You would be able to factor this and solve. That's because our solutions ended up being nice integers. But these ones, ended up being a complex number for the solutions or ended up being an irrational number. You would not be able to factor those over the integers. So if we end up with an integer solution or a rational solution, like if I ended up with, say x equals, um, I don't know, 3/2 or -1/2 or something like that. Those are the kind that we would be able to solve by the factoring method. But these ones that end up as irrational numbers with some, funky square root in them, or with complex number solutions, these are the types of problems we can solve with completing the square that we could not solve by factoring. And one last one, 7x squared plus 4x equals -5. And we might want to jump the gun here and be like, oh, 4x, that works really nicely. Is this like 7x plus 2 all squared? Be careful, because if we're not careful with the details, well, what are my firsts here? 7x times 7x is actually 49x squared. So I don't really want to do that. I want to start by getting rid of this 7, this coefficient of x squared. I have isolated my variable terms. I got the constant onto the other side. But now I want to divide by the coefficient of x squared. So x squared plus 4/7 x equals -5/7. And now I want to say, okay, this is my coefficient of the linear term. This would be like 2r from how I wrote it up here. So if 2r is 4/7, then r has to be 2/7. So I want this left-hand side to be like x plus 2/7 squared. If I do that, my firsts are going to be x times x, or x squared. My outside is going to be x times 2/7. My inside is going to be plus 2/7 x. That gives me plus 4/7 x. My last 2/7 times 2/7 is going to be 4/49. 2/7 squared. That's added on the left-hand side. I better add that on to the right-hand side as well. I'll write it this way just so it's a little easier to see where it's coming from. So that is the constant term that from this line to that one, I've added onto the left side to make that perfect square. I better add that on over here as well. And on the right, I have -5/7 plus 4/7 squared, or that's -35 over 7 squared plus 4/7 squared, or that is -31 over 7 squared. I'll write it that way because I know I'm going to square root in just a minute here. I want to square root both sides. X plus 2/7, getting rid of the square root over there, is square root of -31 over 7 squared. And since I did the equation solving step of square rooting both sides, I can lose a solution if I do that. I better put in plus or minus. I kind of put that plus or minus kind of far away, but better put in plus or minus. So I maintain those two solutions. And now I subtract 2/7. This square root of a negative whatever is I times square root of positive of that. I have square root of 31 over, and the square root of 7 squared is just 7. So my answers here, x equals -2/7 plus or minus square root of 31/7 times I. Okay, so that was the first couple sections of chapter 9. Let me stop the recording.